One of the most powerful ideas in all of physics. It's called the Boltzmann Equation, and it's an incredible tool that helps us find beautiful, predictable order in what looks like, well, complete and utter chaos.
Think about that question. How do you find a predictable pattern in something that seems totally random? How could you possibly write a rule for something that, by its very nature, seems to have no rules at all? Well, this is the exact problem that one physicist decided to take on.
Just try to picture it. A single puff of steam. Inside are trillions upon trillions of tiny particles, all zipping around, bouncing off each other at unimaginable speeds. You couldn't possibly track even one of them, let alone all of them. It is, quite literally, the definition of chaos. But what if there was a hidden order in all that mess?
To find that hidden order, we've got to go back and meet the mind behind the equation, Ludwig Boltzmann, the man who dared to look at that chaos and see a pattern that no one else could.
So Ludwig Boltzmann was this brilliant thinker. He looked at that puff of steam, that system that everyone else saw is just random noise, and he saw something different. He saw a statistical puzzle just waiting to be cracked. He had this idea that, hey, maybe you can't predict what one particle will do, but maybe, just maybe, you could predict the behavior of the whole group.
So, in the late 19th century, Boltzmann basically created a whole new field called statistical mechanics. It's all about using probability to figure out how huge groups of particles act. And this new way of thinking led him to create his famous equation in 1872. Its legacy? Oh, it's massive. It provides the actual mathematical proof for one of the most fundamental laws in science, the second law of thermodynamics. You know, the one that says things in the universe tend to move from order to disorder.
So what does this equation actually do? Well, the best way I've heard it described is to think of it like a bridge, a really important bridge that connects two totally different worlds.
Okay, so here is the official definition. The Boltzmann equation describes the statistical behavior of a thermodynamic system. But here's the really crucial part. It's for systems that are not in a state of equilibrium. All that means is that the system is still changing, it's still in motion. It hasn't settled down into a nice, stable, boring state yet.
And at its very heart, that's what the equation does. It takes the invisible chaos of all those individual little particles and it connects it, it bridges it to the world we can actually see and measure, things like temperature and pressure. It's the link between two completely different scales of reality.
And here's that bridge in action. On one side, you have the microscopic chaos, all those random high-speed collisions. And on the other side, you get macroscopic order, the things we can actually stick a thermometer in and measure, like the temperature of a gas or the pressure building up in a container. The Boltzmann equation is the thing that lets you get from one side to the other.
So I'm going to say it again, because this is so important. The whole point of this equation is to describe systems that are still changing, that are still evolving. Think about that puff of steam. The equation is for the moment right after it leaves the kettle, before it's had a chance to spread out and cool down. It describes the system while it's on its journey towards a settled state.
Now, let's look at where this idea takes us, because its power goes way, way beyond a puff of steam. This one single equation has sent ripples through almost every field of science you can imagine.
The applications are just staggering. In fluid dynamics, it helps us figure out how air flows over an airplane wing. In quantum theory, it's used to model what particle collisions were like in the first few seconds of the universe. It's even used in astronomy to understand how stars move around inside entire galaxies. It is truly everywhere.
But to really get a feel for its predictive power, let's get specific. How powerful is this math really? Well, it's powerful enough to help us decode the secrets of the stars themselves.
You see, using the Boltzmann equation, scientists can ask these incredibly precise questions. Questions like, okay, at what exact temperature, deep inside a star, will the hydrogen atoms get so energized that they jump to a specific higher energy level? And the equation just spits out the answer. In one famous case, that temperature is a mind-boggling 66,000 Kelvin. Now just stop and think about that. An equation dreamed up in the 1800s can tell us the precise conditions inside a star millions of miles away. That's just incredible.
So let's bring this all together. After all this time, why does this one single equation still matter so much?
Well, because it gives us a mathematical tool to find certainty in uncertainty. It proves that even in the most chaotic, random-looking systems, there are predictable statistical patterns hiding in there, if you just know how to look for them. It finds the signal in the noise.
But beyond all its practical uses, its greatest legacy is probably how it changed our whole philosophy of science. It showed us that some of the most basic laws of the universe, like how heat flows,
aren't some kind of rigid, absolute command. Nope, they are simply overwhelming statistical probabilities. And that insight completely changed how we see the world.
Boltzmann gave us a key to unlock the statistical nature of the universe. And it kind of leaves you with this final lingering thought. If this much order can be found in a simple puff of steam, or in the heart of a distant star, what other incredible secrets are still out there, just waiting to be discovered, hidden in the beautiful mathematics of chaos?